Houston, we have a problem. This year's game is about April tags, but the best April tag camera that's so easy to use is sold out. No big deal, we can make one. What we need is a Raspberry Pi computer, and a couple of USB cameras, or even one. Okay, 1 hour later, the Raspberry Pi computer is assembled, and I duct tape a USB camera to it. Let's plug it in. Somewhere here. This will be our limelight. Now we'll need a network cable. Plug it into here, like so. This will plug into the robot. Finally, we need to take a micro SD card, and we need to download PhotonVision onto it, which I will show you in just a moment. Micro SD card plugs into the Raspberry Pi here, like so. Hey, so how do we actually put PhotonVision onto this SD card? Google PhotonVision install. Click install. Good idea. Install the latest image of PhotonVision for your coprocessor. We have a Raspberry Pi 4 or Raspberry Pi 5, so download the latest pre-configured image. But before we do this, we actually need to get Balena Etcher to flash things. So Balena Etcher setup, downloading for Windows. There we go, installed. I have Balena Etcher here. Do it again. PhotonVision install. Click install for PhotonVision. Download the latest image of PhotonVision for my Raspberry Pi. So this is the latest and greatest. And all we have to do is we have to go to the list of images and download the Raspberry Pi image, this one. Now, if you plan to use the 2024 version of Robot Pi, then you need to go to the previous release and find the 2024. Your choice. I'm choosing the 2024 release because I'm going to be using the 2024 Robot Pi. So that looks like the release that we want. And so we open the assets of that release, and we can download the Raspberry Pi image for PhotonVision 2024. Downloading, downloading, downloading. There we go. We have it. Now I need to open Balena Etcher. And to say flash from file. Flash from this download file. PhotonVision 2024. Open. Now I need to put it onto this micro SD card. But I need to put it into my computer. Plugged into the computer. Put it on this SD card. Select flash. I've completed. Time to take this card out and put it into the Raspberry Pi. Okay, we're back in this garage for testing. And look at what I have done. I actually had two USB cameras in my closet. So I taped one USB camera to the side of the Raspberry Pi and the other USB camera to the front of the Raspberry Pi. And we just have to connect them like so to the USB ports at the end of it. The SD card has already been installed, so it's just a matter of powering it on. Okay, the fan is spinning, the Raspberry Pi is powering on. It will take a couple of minutes for the image to work, I think. But then we should be able to drive this robot with it and see if it can follow the April tag on the wall. Oh, and of course I forgot one very important detail. Here in the back is a network cable going into the Raspberry Pi. This network cable connects into the robot radio, so that this Raspberry Pi is simply in the robot network, just like Limelight was. And Limelight is in the front, but I have turned it off. Okay, time to connect to the robot Wi-Fi and see if we can find the camera on that network, our new PhotonVision camera. The robot Wi-Fi is connected, and the driving station is communicating with the robot. Let's see if we can find the new camera here. We type in PhotonVision.local 5800. There we go. This is the camera. PhotonVision.local 5800. So it found both cameras, and the camera in the front is called USB camera, but we don't see anything in it because the type is reflective. What we need to do is we need to switch this camera to April tag. Yes, I am sure. And now we have a picture, but the picture is very bright. What you would do is you enable auto exposure. Very good. And auto exposure is just a very easy setting to use. It's looking at an April tag right now, as you can see, but it's not detecting it. That's because we need to go to the April tag tab here and say, this is not April tag 16, this is April tag 36. And yes, now we have a detection. So let's rename this camera into front camera. And let's call this pipeline. You can just edit them in here. Front, April tag 36, is 40. And that's right, we're supposed to be able to change the resolution of the camera. If we go back to the input tab for this camera, we can see that the camera resolution is 320, which is great, but if you want localization, you probably want 640. And so I'm gonna choose MJPEG 640 400 at 20 frames per second, which is good enough for what we want to do. And this is saved. Now we have another camera here. It's called Arducam, and it's also not showing anything because it's in reflective pipeline. We switch it to April tag. Yes, I'm sure. But it appears to be flipped upside down, which is obviously not great. So what we can do is we can go down and we can say orientation is 180. Now we have the correct orientation and everything is good. We can also go and change. So there is a cable on the background here, and I'm gonna remove the cable in a moment. We can keep the resolution at 320 if we want to. And look, this Arducam camera is capable of giving us 60 frames per second. This is not bad. We can also ask it to detect April tag 36. So if I rotate the robot like this, so that the side camera is looking at the April tag, hey, it is detected. What's great about PhotonVision is right here on this website, you can see where the target has been detected. And yaw is kind of like X. So if the tag is all the way on the left, the X is positive, 13 degrees. And if the target is all the way on the right, the x is negative, minus 17 degrees. So I know for the fact that this camera has a 70-degree field of view, which is the difference between the rightmost object and the leftmost object that it can see is 70 degrees, more or less. You have to make sure that this is correct. Front camera that we have is also a 70-degree camera, so this is correct. But if you're using a wider or a narrower camera, you have to set this in the Cameras tab of PhotonVision in here. So let's rename the side camera into the left camera. Left camera of the robot. And we can call this pipeline left April tag 36 with a resolution of 320. Save. Very good. So we have two robot cameras working at very impressive frames per second, just using a Raspberry Pi. Let's see if the robot can see the output of those cameras. What we need to do is we need to go to Elastic, and we need to check. We need to try to add widget for those cameras. So I click on Add Widget, I go to Camera Publisher, and we only see Limelight, and this is just from the history, because it's not plugged in right now. Why is this photon camera not communicating with the robot network tables? What we need to do is we need to go to the settings in here and see what's going on. The network tables server address is not set or invalid because and network tables is unable to connect. You can see not connected to the network tables server of the robot. Why? Because we forgot to put in the team number, which can get converted into the network tables server address. Also, if you have multiple Raspberry Pi cameras, what you want to do is you want to give them different names. But because we only have one here, just with two sensors, we can keep the name of the Raspberry Pi as PhotonVision. So, team number is 714, save, and what we should see is that network tables is now connected 10.7.14.2, whatever. This camera is now communicating with the robot. So if we go back to Elastic, in Camera Publisher, we see all sorts of cameras that we had in mind. What can we do? For example, we can add the feed from the camera by opening Camera Publisher in Elastic and moving it into here. So this is the feed from the side camera, and this could be the feed from the front camera. Now we have a driver window, which drivers can use. If I move the robot, the picture moves. Now, if you want to see how tags are detected, you have to pick the output video. So if I put the output video in here, you can see the tag is detected on it. Tag number 1. And needless to say, buying a Raspberry Pi is much cheaper than buying a Limelight camera. And hey, you have 2 video feeds for the price of 1. Raspberry Pi is like $60. Innomaker Global Shutter camera is $40. Total is 100. So let's go back to this web page about autonomous driving and aiming commands. The link is in the description. Here in the section 5, we can see what to do to use vision cameras to navigate. What we want to do is we want to approach this visible game piece or a tag using camera. This code works with Limelight or PhotonVision cameras from here. Very good. Because what we have in our robot right now from the previous video is we have a Limelight camera subsystem, but we don't have a PhotonVision camera, so we need to add this. this is what we do. This is the example code for Limelight, which we have already added. Now we can add the example code for PhotonVision camera. Copy, and it should go into subsystems / PhotonVision camera.py. PhotonVision camera.py. Add. Very good. This is done. Now we need to add this PhotonVision camera to the robot. This must go into pyproject.toml. So let's go to our pyproject.toml. We already have it. And now inside of robot container.py, where we put all the subsystems, we need to make sure to put PhotonVision camera instead of Limelight camera. So we go to robot container.py, and we need to find the init function where we put all the robot subsystems. So let's say we don't have Limelight, and instead we have PhotonVision camera. What did we call it? We called it front_camera. That's done. And because we already have object following somewhere in here as an auto using the camera, I think it will just work. Yes, take a look here down at the bottom in robot container.py. When we configure autos, we have one auto called approach tag, which is written out in this get approach tag command function, this one. What we do here is we set the start pose, then run some sort of trajectory. We probably don't need it for this test. And then we follow the tag using self.camera, which we just now assigned to be the photon camera. So maybe our command can be set start pose and then follow tag. Let's see if this works with the camera that we have just installed. Oh, one last detail. Since we have two cameras on an actual robot, let's have two cameras in the code too. So if we go back to the init function where we added the front camera and we called it self.camera, we can also add another camera, self.left camera, and add the other camera that we have on this robot also as a PhotonVision camera, left_camera. Since we are connected to the robot Wi-Fi, let's deploy this code onto the robot. Success. Driver station looks happy. And so we can go to Elastic and choose the auto to approach tag using the front camera that you can see is looking at it. Going to autonomous and enabling. Perfect. Robot drove exactly to the tag. Now let's do something fun. So far we have been looking at autonomous driving, but what about driving with buttons? What if I want to push the button A and I want the robot to find an April tag and then to drive to an April tag and then to even align itself exactly against an April tag and then push into this April tag so that maybe it can drop a coral or hang it on a hook. So when the A button is pressed. So we're going to take the A button of the joystick like this. Second, let's see what kind of things that we want to do or when this button is pressed. First, we want the robot to find an April tag. So from commands, find object, import, find object. We're going to have a command that's called find tag. I just came up with a name. Find tag equals find object. What do we need to give it? We need to say self.camera, self.drivetrain, which is robot drive in this case. What robot will be doing is it will be turning by, for example, 30 degrees at a time until it sees an object in the camera. So we can say turn degrees equals minus 30. Minus means it's going to be making right turns. With a plus, it would have been left turns. Turn speed is 1.0, this is fine, and it will wait between those turns, that is also fine. Now, after it finds the tag, actually, before it finds the tag, it needs to know what to look for. This is called setting of the pipeline. From commands dot set pipeline, set camera pipeline, import set camera pipeline. What the heck are the pipelines? Let's go to PhotonVision website. The idea is the pipeline has to do with what kind of object you want to detect. If you want to detect an April tag, you just need to specify that you want to detect an April tag, and you can save this pipeline under a new name. And it could be pipeline number 0 for you. But you can also detect objects. For example, pieces like this. And this could be your pipeline number 1 or pipeline number 2. What you need to do is you will need to select object detection in your pipeline configuration. In other words, pipeline is what kind of objects you want to detect. You can make it so that pipeline 0 is April tags, pipeline 1 is game pieces, and maybe pipeline 2 could be something else. With PhotonVision, you can also filter which April tags you want. For example, April tag 1 and 4, and only those. We'll talk about this a little later. Anyway, so first you want to tell your camera what kind of objects you're looking for. This is called set camera pipeline. Set pipeline. We're going to create a command called set pipeline. Is set camera pipeline on self that camera. And what else does it need to know? It just needs to know the camera and which pipeline index to use. We only have one pipeline in here, so the index is 0. Then we're going to find object, and then we're going to follow that object, approach that object. Commands.follow object, import, follow object, and when to stop. What I want to do is I want to approach this tag until it becomes so big in my camera that it takes 8% of the screen, which is pretty close. So follow object will be a command that's follow object. We need to give it a camera, self.camera, self.drivetrain. And what we need to do is we need to specify stop when. Stop when equals. We should be stopping when max size is 8.0% of the screen. Now, after we are done getting close to the tag, wouldn't it be awesome if the robot just aligns itself exactly to the tag by using its swerve functionality? For example, if it is not facing tag directly, or if it's a little to the left, a little to the right, would be great if it just kind of centers itself, looking exactly at the tag. So from commands dot align with tag, import align with tag. Align with tag equals align with tag self dot what do we need to give it? Align with tag is a function that takes camera, drivetrain, and pretty much this is all that we need to give it. Self dot camera, self dot drivetrain. And if we want the robot to push forward after aligning with the tag, then we need to say push forward seconds equals, for example, 0.8. We want the robot to push forward for 0.8 seconds after doing this, after aligning itself with the tag. Okay, so let's connect all of those commands together and then put them onto the A button. So we say A button dot while true. We're going to say set pipeline while A button is pressed. We want to do this. We want to set pipeline and then find tag and then follow object and then align with tag. So when the A button is pressed and while it is pressed, this complex command will be running. Let's see if it works. Deploy to the robot. So this looks like an autonomous command, but we don't have to use it in the autonomous mode. We can use it in teleop by binding it to a button, just like we did. I'm switching the robot to teleoperated mode. I'm enabling it. And maybe let's look at the video because it's a little bit more fun this way on the elastic dartboard. And, I'm going to be pushing the A button and see what robot is doing. First, it should be finding the tag and then getting to the tag and then aligning itself and pushing forward. Pushing the A button. 3, 2, 1. Looking. Got to the tag and pushed. And you can already see which mistake I have made. I have forgotten to set speed on object following to a so it actually sped to the tag with the maximum possible speed. The code was redeployed with the slower speed for object following, and I'm going to push the A button in 3, 2, 1. Look what happens. It's looking for the tag. It found the tag. It's getting to the tag. Itself for the tag and pushing forward. Let's talk about Reefscape. In Reefscape, you want your robot to go to a very specific tag, at least during the autonomous, because hopefully in your alliance you have agreement. My robot goes to this tag and does that. Your robot goes to this tag and does this. So how do you make sure in PhotonVision that the robot goes to tag number 3 and not tag number 8? What if I want the robot to only find tag number 1 and tag number 4, or only tag number 7 and no other tags? What do I do in PhotonVision? To do this, we need to slightly modify this code that we wrote, because this command will find all tags that are given in pipeline index number 0, which is all April tags of a particular family. What if we only want to find April tag 1 and tag 4, or maybe just tag 1? What we need to do is we need to go back to this adding camera document, and we have a third example here. Example code for PhotonVision camera that will only give you the tag IDs that you specified. For example, just tag 3 and tag 8. We have to install the official PhotonVision library. So this goes to your PyProject.toml. We have to download the PhotonLibPy, which is the official library for PhotonVision. So let's go to our PyProject.toml, which is the list of things to download onto the robot. And at the end, we have this requirement, a list of requirements, PyNT core and Photon. Now we have to add PhotonLibPy in here. And if you have downloaded the 2025 version of the PhotonVision onto your Raspberry Pi, then you must change this version string to be a 2025 0B, and it will work. We have 2024 version, so we're using this. Next, looks like we need to add this to the end of the requirements.txt. So, okay, I'm going to add those to the requirements. And we don't need the comment. I'm gonna put PhotonLib Pi here, and then PyNT core afterwards. And finally, we need to define another kind of camera, photon tag camera, which can filter by April tag ID. So we're gonna put it into subsystems photon tag camera. This is the code. It's not all that different from the PhotonVision camera that we looked at before, but we must put it into subsystems. Here we have the PhotonVision camera, but we're going to add another one. New Python file, photon tag camera.py. Paste all of this code, and this is kind of what we need. But instead of using PhotonVision camera, we must be using photon tag camera right now. So we go back to the robot container, which everybody will edit for the competition. And previously we were using PhotonVision camera in here. The self.camera equals PhotonVision camera, right? That's what we had, PhotonVision camera. Now we're going to import another camera from subsystems, photon tag camera, import photon tag camera. And both cameras will be defined as photon tag camera. Why is photon tag camera better? Because what we can do, it has another method called set only tag IDs. So we can say, hey, you're only going to be looking at tag IDs number 1 and 4. You can do it right from the start when the camera is created, which is right here. You can say, hey, self.camera, set only tag IDs 1, 4, 5. You can use regular brackets or square brackets, it will still work. But then this camera will be stuck in this mode forever, for the whole process. If you want to change which tags you want to detect, then you probably want to do it in a command, and this is called an instant command. You can call any function using an instant command. So let's just say from wpi lib import from commands to, import instant command. And we're going to create a command that switches the camera to only detect tags 1 and 4. So set specific tags we want. I'm gonna call it this way. It's going to be an instant command. And we need to tell it what to do. So obviously we want self.camera.set only tag IDs 1 and 4. This, however, will not work because then this function will be called right at the time when we created the command. But we want this function to be called when the button is pressed for this command. If we want some function to be called later, we must say in Python lambda. Now this function will be called later. So instead, when we create a command of what to do when the A button is pressed, now we have one more step to do. Set specific tags we want, then set pipeline, then all of this. Set specific tags we want, and then set pipeline, and then all of this. And this will work if you want to follow specific targets. Thank you for listening. This was a lot. One question that you might have, hey, Raspberry Pi needs 5 volt over USB, but the robot battery is 12 volt. What do we do? The easiest way to solve this is you can buy a buck converter from 12 volt to 5 volt USB. What's important, however, is that if you're using Raspberry Pi 5, you want 5 amps, because Raspberry Pi 5 plus a couple of cameras and maybe you're gonna connect the edge chip to it, it's gonna eat more than 3 amps. So make sure to get the right converter. Problem with this converter that I see right now is it actually will not work if the voltage temporarily drops to 8 volts when the robot is starting or doing something complicated, when there is voltage sag on your battery. Some converters support smaller voltages, which can happen with your robot if it's doing a lot of work and the battery temporarily sagged to 8 volt. The problem with this specific product that I see on Amazon is it's not going to give you 5 amps. It's going to give you 5 USB outputs, but each one is limited at 2.4 amps. So it's not ideal, but maybe if you're using Raspberry Pi 4 or Raspberry Pi 5 with just one camera, that might still work for you. Um, Please check our team website, FRC714.com. Our students are actually working on making a converter that's lower voltages and going to give you 5 amps, which hopefully is the ideal power your Raspberry Pis for FRC competition.